Okay, in discussing linear dependence and independence, I want to go back to sort of a basic algebra class. And I'm just going to write down this sort of generic equation. And just as a way of reminding you, these are the variables and these are the constant coefficients. And we call this a linear combination of the variables x, y, and z. And there are a couple of different ways for this equation to be true. Either, let's see, I'll do it as a bullet list. Either A, B, and C are all equal to 0, or A, B, and C are not all equal to 0. That may seem trivial, but I'm getting at what's the definition of linear and linearly independent here. So one of these two things has to be true. Either all three of the coefficients here are 0, or another way to say this would be to say that at least one is not 0. So let's assume for the moment that A is not 0. Then I can use this really cool phrase that I've used once or twice before, without loss of generality. I just want you to be exposed to some of these expressions that you will hear throughout your mathematical careers at one point or another. Generality. I can say that without loss of generality. What that means is that I'm assuming A is not equal to 0, but it would, once I've shown you what I'm going to show you down here, I don't need to show you the same thing for B and C because the same idea holds. So I'm generalizing it, just using A as the sort of the random choice. And I don't lose the generality of the statement that the same holds for B and the same holds for C. All right, so assuming that A is not 0, but that B and C are, then I get this equation, AX equals 0. And if A is not 0, then X must be 0, right? X is an unknown variable number. A is some constant that I don't know. If A is not 0, then X, the value of X, must be 0 to make this statement true. So, and that's the trivial case, right? We're not really interested in this. We're trying to figure out what we can say about A, B, and C. So this isn't really very helpful. The other possibility here is that A and B, or A and C, and again, I'm just going to randomly choose A and B, are not 0. Then that means that C could still be 0, but A and B are not. That gives me AX plus BY equals 0. If I subtract BY from both sides and then divide both sides by A, I get X equals negative, and I'm going to write this as B over A times Y. I get that X is just a constant multiple of Y. Okay, so if A, B, and C are all 0, this is clearly true. If A is not 0, I get the trivial case, and I'm not interested in that. If there are two that are not 0, then I get a case where one of the variables x and y can be written as a constant multiple of the other. And so these are the two things that we're really interested in here. A, B, and C are all 0, or two of them are not 0, and one of them, in that case, one can be written as the constant multiple of another. In this case, we say that x, y, and z are linearly independent. And in the other case down here, we say that x and y are linearly dependent. Now, there's a third case here where we have ax plus by plus cz equals 0, where none of A, B, and C are 0. So we have all three variables, or all three constants, A, B, and C, non-zero, in which case we say that x, y, and z are linearly dependent. But I can still break this up into two cases. Either one or two or all three of these are not 0. At least one is not 0. They're not all 0, in which case x, y, and z are dependent. Or all three of A, B, and C are equal to 0, And in that case, we say x, y, and z are linearly independent. So it's two different cases. And remember that what I'm saying here is that this particular equation with the right-hand side being equal to 0 has one of these situations. So this is kind of the definition of linear independence or linear dependence. Your textbook takes a slightly different approach by using K1, K2, K3, and so on instead of A, B, and C, and functions F1, F2, F3, and so on instead of X, Y, and Z. And these are functions of t. I'm going to try to squeeze that in one case. But it's essentially the same thing. X is a function of x, y is a function of y, and so I'm making that an analogy here. Of course, in the textbook case, we have more of these because we're dealing with the nth order case, right? We have all the way up to k sub n, the nth function, but the sum of these is still equal to 0. And what your textbook says is that these functions, remember that the functions are my x, y, and z, are said to be linearly dependent, that's this case down here, if there exists a set of constants, k1 through kn, that's my a, b, and c, that are not all 0, such that this equation equals 0 is true. Okay, so if K1, K2, and all the way up to Kn exists, but they're not all 0, and they make this equation true, then we're in this case here. They're not all 0. So this is the linearly dependent case. And then it goes on to say that the functions f1 through fn are said to be linearly independent by definition simply if they're not dependent. Well, if they're not dependent, it's because constants k1 through kn exist that are not all 0. So for them to be independent, k1 through kn have to be all 0. They all have to be 0. So that's this case here. So it's a slightly different wording. It's a slightly different approach to the definition of linear independence, but it's the same thing. The definition of linear independence is that this equation here is equal to 0 only if a, b, and c, only if the constant coefficients are also all 0. If one of them is not 0, then we say that the functions or the variables x, y, and z are linearly dependent. Let's take a look at an example. There's a problem that you'll be asked to do in the online homework that gives you, I'll tell you what, let's go to another screen and I'll just tell you what the problem is. Okay, so here's the question. If the set of collection of things, x, y, z, w, these are vectors, but we don't need to worry about that in this class, but it doesn't really matter what they are. I'm telling you that they're linearly independent, a linearly independent set in n-dimensional space. Determine whether the set made up of the three things x plus y plus z, and z plus x are linearly independent. Well, if they are, then I can scale them. I can take a multiple of 1, add it to a multiple of the next one, and a multiple of the third one, set that equal to 0, and then for it to be true that this is equal to 0, one of two things has to happen. Either A, B, and C are all 0, or they're not, and there's some other combination going on, right? So what we want, if we want these to be independent, if we think these are linearly independent, then A, B, and C need to all be 0. Well, what does it mean for A, B, or how do we find what A, B, and C are? Whether they have to be 0 or whether they might be something else. And I think what I would do here is just use a little bit of algebra, do some distribution. And then redistribute this so that I have a constant in front of x plus a constant in front of y plus a constant in front of z. And what I'm going to do to figure that out is just recognize that in front of x I have an a, and where is it? There's a c. In front of y I have an a and a b, And in front of z, I have a b and a c. That's going to give me a plus c times x, a plus b times y, and b plus c times z. Now what I have is a linear combination of x, y, and z, right? I have x, y, and z with some variables in front of them. And what I said on the previous screen is that if x, y, and z are linearly independent, then their coefficients in this linear combination must all be equal to 0. All of them must be equal to 0. So these three things then are also true. And if I just take one of these and solve it for one of the variables in terms of the other, I get that. So now I can substitute a negative c in for a here, and that's going to give me negative c plus b equals 0, which tells me that c equals b. And if c equals b, that gives me 2c equals 0, in which case c has to be equal to 0. Well, if c is equal to 0, then guess what? b is also equal to 0. And if b is equal to 0, where am I? If c is equal to 0, then so is a. So I get a equals 0. So in this form, we have that all three of these are equal to 0, implies that the original coefficients here were equal to 0, which means that these three things, x plus y, y plus z, and z plus c, are linearly independent. So that's a kind of a weird one, actually. It's a little bit of an unusual problem, but it's nice that it gets at what it means to be linearly independent. I'll take a look now at a slightly simpler one. This is closer to the ones that you'll see in your textbook for this course. Okay, so here are three functions. f1 of t is 2t minus 3, f2 is 2t squared plus 1, and f3 is 3t squared plus t. And our goal here is to determine whether these three functions are linearly dependent or independent. Well, I can take each one of them. Each one of them is my x, my y, or my z. So there's my x from my previous example. And y, the second function, is 2t squared plus 1. And z is 3t squared plus t. Take each one of those, multiply it by some constant, and set that sum equal to 0. And if a, b, and c, once I've done this algebra here, if a, b, and c have to be 0, all three of them have to be 0 to make this true, then our three functions are linearly independent. So let's do the algebra. 2at minus 3a plus 2bt squared plus b plus 3t squared c plus, let's see, I'll do the c first because that's a constant. That has to equal 0. And then I'm going to combine like terms so that I have the squared terms first. So I'll have 2bt squared plus 3c t squared. And then the t terms, I have 2at plus ct. And then I have a constant term of, instead of a plus, I need a minus there. I have a constant term of minus 3a and a constant term of b. So there's my constant minus 3a, my constant of b. I guess I could have highlighted or identified these in some other way. I've got squared terms here and here. I've got linear terms here and here. And I have constant terms here and here. And I've captured those all now in my new version of the equation. So now I'm going to factor out that t squared. I'll have 2b plus 3c t squared, and then I'll factor out the t. I get 2a plus c times t, and then I forgot my equal 0 up here, and I have the constant. I'll put a plus here, and I'll just go negative 3a plus b equals 0. Now remember that what I'm looking for in this case are what A, B, and C have to be to make this true. I'm not interested in what T is. In fact, what I'm trying to do is show that A, B, and C are all 0 or not. I'd like them to be all 0 because then I have independence, but I don't know what yet at the moment what I'm going to end up with. It doesn't matter what T is as long as it's in the interval in which there are solutions. Well, we haven't really talked about that much in this section, but we did talk about it in a previous section. Let's see, it was section 3.2, which was about the Wronskian, but it was the existence and uniqueness theorem for I believe it was second order. Yes, second order differential equations. And we talked about putting the equation into the form where the initial or the leading coefficient was 1. In other words, if you have to divide through by capital P of t, then sometimes when you divide through by a function, you end up with a function in the denominator of the coefficient of another term, and that means that that denominator can't be 0. So finding some values for t, which will make that denominator not equal to 0, is important. And in particular, we have a differential equation. I think I'll just write one out over here. P of t times y double prime, this is for the second order case, plus q of t times y prime plus r of t times y equals, because we're dealing with homogeneous equations, I'll just go with 0. If I divide through by P of t and define, of course I have to divide both sides, that cancels. But if I define Q over P as little p and define R over P as little q, for example, I end up with y double prime plus P of t, little p of t times y prime plus little q of t times y equals 0. And what I'm getting at here is that this denominator can't be 0, right? So that helps us to identify the interval on which there are solutions to our equation. We're not doing that here because we're not dealing with a differential equation. I've just given you 3 random functions and asked you to determine whether those functions are independent. If I divide through by this constant here, I would get something of a similar form, but notice that I'm dealing with t squared, not the second derivative of some function called t. So I don't need to worry about that in this context, but I will need to worry about it in the context of solving a differential equation. So just keep that in mind as we go forward. So what I need to do here is figure out how all 3 of these can be 0 if, again, what I'm looking for is the values for A, B, and C, but it doesn't matter which values I use for T. So let's just choose some nice random values. Let me rewrite this as 2B plus 3C times, oops, I forgot my C there, times something squared plus 2A plus C times something plus negative 3A plus B equals 0. And I'm going to do, for my first one, I'm just going to let T equal 0. Because it's easy, right? It's convenient. And when that's the case, right, when t equals 0, then clearly this first term becomes 0, the second term becomes 0, and I end up with, I'll tell you what, I'm going to put this over here. I end up with negative 3a plus b equals 0. Okay, and so then b, I could say, is equal to 3a. B is just a multiple of A. So already I can tell that there's a problem, right? I have A and B, one of them is a multiple of the other. So let's carry on. If T is 0, let's erase the 0 and put a different value in there. What if T is 1? Then I get 1 squared is 1. So I get 2b plus 3c times 1 plus 2a plus c times 1 plus negative 3a plus b. And that still has to add up to 0. Well, let's see, I've got a here and here. B there and there, and C there and there. So I have 2a minus 3a is negative a. B's are 2b plus b, I have plus 3b. And 3c plus c is 4c. Now in order for that to be 0, a, b, and c could be a lot of different things. B and c are probably going to be fractions. But even if b and c were both 1, even if they were both equal, and let's just say they were 1, a would have to be something else. And they're certainly not 0. B and C could be 0, in which case that tells us that these go to 0, and A has to be equal to 0. But that's not the only solution to this equation. So we have a problem. I could take a third value of, I'll just use -1. So I'll take a third value for t. Now I don't have to do this because I've already determined that there are multiple solutions to this equation. There are multiple values for A, B, and C. If all of them are 0, that's one thing, but that's not the only solution. So what that tells me is that the setup that I provided here has multiple solutions. The only solution is not the 0 solution, and therefore these three functions are linearly dependent. And what I want to ask myself about this now is, what does that mean in the context of differential equations? And the answer is this. Instead of working with functions like t squared or just generic functions like x, y, and z, what if the functions that I'm dealing with are solutions to a differential equation? I'll just stick with 3 for right now. These equate to our, or analogous to our x, y, and z. If it's true that, and in fact I'm going to use k here again because your textbook does, if I can write a linear combination of these three functions and that combination equals 0 means that all three of my k values have to equal 0, then that tells me that my solutions, y1, y2, and y3, are linearly independent. And to find out what those k values are, I would probably do something like this. Take the 0th, first, and second derivatives. Remember, I get to stop one short because I need 3 equations and 3 unknowns. You don't actually need to do this step. I'm just writing it out to remind you of where this next piece comes from. This produces a coefficient matrix of y1. Remember, I'm looking for the unknowns of k1, k2, and k3. So I have a y1, a y2, and a y3, a y1 prime, and so on. And when I take the determinant of this matrix, we call this thing the Wronskian. So this is the Wronskian of y1, y2, and y3. And we want that to not be equal to 0. If it is equal to 0, then my functions y1, y2, and y3 are not independent. But if it is equal to 0, if it's not equal to 0, then y1, y2, and y3, those solutions that I originally claim are individual solutions to the differential equation, are linearly independent. And when that's true, we say that the set containing the solutions y1, y2, and y3 form a fundamental set of solutions to an equation such as this one here. Now, I've done all of this based on the idea that we're working with a third order differential equation, just to kind of keep it on the small side so that the theory behind all of this isn't too difficult to take in. The examples I gave in the previous video, finding the Wronskian was actually indefinitely large. We had n entries in each row and each column. So this is just a description of what's going on in the case of a third order differential equation. But remember that you can have more or fewer solutions to work with, right? We've been working with second order differential equations until now, and that's just the case where n equals 2. All right, I'm going to highlight a couple of things here. This set right here, I'm going to say is a fundamental subset, or sorry, fundamental set of solutions to this equation here, and I'm going to highlight the equation as well. There's a theorem in our textbook. It's called theorem 4.1.3, which is another romantic name for a theorem. I'm being very sarcastic. And what that says is if there's a collection of equations or a collection of functions, and that collection of functions forms a fundamental set to this equation, then those three functions, or those n functions, are linearly independent. Equally, if those three equations are linearly independent, then they form a fundamental set. So this idea of fundamental set, for those of you who've taken linear algebra, we're just talking about a basis, right? These may not be the only three solutions here. They may not be the only functions that are linearly dependent and satisfy the initial conditions. But they certainly do qualify as a set, a fundamental set, which in linear algebra we would call a basis, to this equation, or to equation of this form, if they're linearly independent. And if they are linearly independent, then they form a fundamental set. So those two statements go both ways. If the collection is linearly independent, then that collection forms a fundamental set of solutions. If we have a fundamental set of solutions, then the things in that set are linearly independent. And that's pretty much it for this video. I apologize for its length. Very close to an hour. I'll try to make a shorter one at some point in the future. The good news is that the next video is the last one, and it should be really quite short.